Hello everyone. Today I'm going to talk about photoelectric effect and why it's so important in the field of science. The photoelectric effect refers to the phenomena where light is shining on a metal surface. When it shines, it causes electrons to eject from that surface. And these are small the blue balls, they are electrons. So as you see, as we shine the light, it's on this metal surface. This metal surface start ejecting the electrons. This is called the photoelectric effect. So, according to the classical physics, it describes that light is purely as a wave. It's a wave. It said that the energy of light is spread smoothly over the wavefront, just like water waves deliver energy continuously to a shore. According to this view, shining a more intense or brighter light should deliver more energy to the metal surface. It shouldn't matter what's the color of that incoming light or frequency of the incoming light. It only depends on the intensity. So the classical theory predicted that if you use very intense light, even at low frequency, you should eventually eject electrons by pumping in enough energy over the time. So what's the problem? The problem is, however, this is not what experiments showed. Just like the black body radiation, as I mentioned it before. So this photoelectric effect also is showed different experimentally in comparison with the theory. So what experiment showed? The experiment found out that no electrons are ejected at all below a certain frequency threshold. So no matter how intense, how high intensity it is, if the frequency is low, the electrons were not ejected. However, according to classical physics, where I just mentioned it, that it doesn't depend on the frequency, it depends on the intensity. However, the experiment showed that it really depends on the intensity. Above the threshold frequency, electrons are ejected, uh, and then further increasing the frequency, actually, it increases the kinetic energy. Okay, so increasing the kinetic energy, while increasing the intensity when we keep making higher and brighter intense, it only increases the number of electrons emitted, but not their energy. So we can draw it as a diagram. Scientists like the diagram. We have the x-axis, which is the frequency, the mu, and then y-axis, we can label it as a kinetic energy. So what happens is we have this minimum frequency, also called the work function. So the work function, we should have the high enough. As we increase the energy from here, it doesn't really happen anything. Only when we reach this point, the work function or the very minimum frequency, then it starts ejecting the electrons from the surface. Further increasing the frequency, it starts increasing the kinetic energy. So this is the diagram, how it works, how it's showing. So if the photon's energy is greater than the work function, it gives electrons enough to break free, only at a certain frequency. The extra energy left over, as we keep increasing the frequency, and when I say energy, always remember that energy is equal to h mu, so energy is directly proportional to the frequency. So when I say high energy, that means high frequency. So that extra energy or extra frequency as left over becomes the electron's kinetic energy. So the quantum physics explains this by treating light not just as a wave, but as a photons, particles. And so each electron absorbs the energy of a single photon. If the photon's energy is below that metal's work function, nothing happens, even at high frequency. No matter how make your frequency high, that earlier was mentioned by classical physics. So if the photon's energy exceeds the work function, The excess energy becomes the kinetic energy of the emitted electrons. That explains why frequency determines whether the electrons are ejected, while intensity controls only the number of electrons that are emitted. More photons means more electrons, but not more energy per electrons.